So what are we going to be doing in this video? Well, firstly we're going to look at anti-reflective coatings, which are a bit of an add-on to what we did in the last video, which was thin film interference. We're going to then look at a phenomena called resolution and resolvence. And then lastly, we're going to do a bit on Doppler shift. And then that will be the end of topic 9. So non-reflective coatings or anti-reflective coatings are usually put on things like glasses to try and reduce this annoying glare that you get. The premise is such that if you can get rid of the reflection aspects of transparent materials, then what you can see much better is the light that comes through. So for example, in the glasses here, you can see the eyes much better than in this one. So we have to try and figure out a way to get rid of the reflection of the surface in order to improve the transparency of the material. Just as a little side note here, these very accurate pictures are from a physics website, and these are from an advert for non-reflective coating, which produce laughably effective effects, but unfortunately rather unrealistic. So bear that in mind if you need to buy some non-reflective coating for your glasses. Don't believe the adverts. So how is this going to work? Well, if we have a look at the reflection situation, we have two materials now. This is our glass. Okay, so you imagine your glasses. That's each one. And this is the coating. And the refractive indexes are as follows. You've got the refractive index of air, which is 1, which is less than the refractive index of the coating, which is 1.4, and the refractive index of the glass, which is 1.6. So remember the rule, as you go from a low refractive index to a high refractive index, you're going to get a phase difference, like your reflecting wave is going to flip over. So that was a problem before because it happened on one surface and not the other. But here it's going to be happening on both surfaces. So both transfers or both interfaces are from low to high refractive index. So what does that mean? Well, as this one reflects, its phase difference becomes pi over 2. But the wave continues, and when it reflects again, there's another pi over lambda over 2. I know I said pi over 2, I meant lambda over 2. There's another phase shift. So by the time they actually get out here, they're back in phase. So that would give us a constructive situation. Now, what we want is for that wave to get back to this point here out of phase. Why? Because as we mentioned before, if they destructively interfere, as your eye receives the light, you will see nothing. And if you see nothing, then the light that's coming through the glass will take priority. You'll be able to see it nicely. It won't be interfered with by all this reflection. So we need to somehow manage to make sure that the rays of light, when they get to here, they become lambda over 2 out of phase. So how are we going to do that? Well, let's look at this distance d. So the light that goes through the coating and back travels a distance of 2d. In order for there to be destructive interference at this point, it has to be equal to lambda over 2. So that means that the distance, in order for that to happen, the distance as in the depth of this coating, should be equal to lambda over 4. Okay, I hope that follows on clearly. Okay, and that's pretty much all they can ask. There's not an awful lot more you can be pushed on in this section. Okay, so last point is interference at oblique angles. If you see situations like oil on water, giving you all these different colours, very pretty colours and things like that. It's because we don't have this nice, perfect reflection situation with all the lines of refraction all coming out at the same angle. You get them in all different colours and all different directions. So the reflection does not have the same angle. Okay, so you do not have the same angle. Okay, so you have different path differences for each section along here. So you might have a path difference. So for example, the path difference between this ray and this ray is going to be different to the path difference between that one and that one. So constructive interference will happen at different wavelengths. So you might get a blue on this side or a red on this side. You get varying different colours. And not only that, the oil film is not the same uniform depth. So again, that causes all this curving shape. All these different shapes and directions are due to the oil having a different depth, which means that your constructive and destructive interference occurs at different points. Now let's go on to resolution. Now, resolution is an explanation for why you can see certain things as separate objects the closer they are. Now, the actual point we're going to focus on is the point when you just about see two distinct points as separate. The really basic illustration of this is when you see car headlights from a distance. When they're really far away, your eye can't tell that they are two distinct lights. There is a certain key point when you can just about make out two different lights in the distance, and then after that, as they get closer, you can definitely see how separate they are. But we're going to focus on that point just when you resolve the two lights as two separate entities. So what is this all about? Well, you remember, and I hope you do because it was only last week, single slit diffraction. The light coming through a single gap and showing bright and dark fringes on a surface. So let me just draw those out. So this is a very rough sketch of the intensity of these peaks that you normally get. So that's in single slit diffraction. Now, this is exactly the same idea, but we're looking at a circular slit instead of a slit of size D. So we're going to be looking at a slit that is round and has a diameter of D. Now, what has this got to do with diffraction, single slit diffraction? Well, your eye is basically a circular slit, and you basically focus things on the back of your eye, on the retina, using this diffraction idea. So light that goes through your pupil here will show a trace which is very similar to the one that you get with single slit diffraction. So therefore we're using the same idea. Now, what has this got to do with separating out two images that are very close together? There is a critical point at which you cannot separate two objects because the light from one of those diffraction patterns is overlapping the other diffraction pattern. So if you could imagine these two as being car headlights, here we have a perfect situation because they're both distinct objects that are reflecting and sending the light for you to focus and have as two separate objects on the back of your eyeball. Now, if that light from those two objects is too close together, say for example here, so that the peaks overlap, all you will end up seeing is one big splodgy mess. So what you have to do is to get the separation just right, if you could get the maxima or the maximum peak to overlap with the minima from the second peak, you see, you can just about then make out those two objects as separate, right? So this would be one car headlight. The main peak would be focusing on the back of your eyeball, but it would be nice and distinct because the other object's minima just happens to be lined up with it. Now, this point is a perfect point, and that would happen at something called the Rayleigh criterion, which is a condition whereby the angle between the two objects, so if this is your eye, okay, and here are the two objects, so this angle has to be greater than a certain condition that we'll look at now. So the next slide will be about the Rayleigh criterion. Now the relationship to distinguish these two distances is a very, very simple one. You can just about separate or resolve through a circular aperture if there is an angular separation of 1.22 lambda over b. Now the nice thing about this topic is the proof for this is so absurdly, ridiculously difficult that you don't even have to look at it. This is one time that you just get the formula, you just have to understand it, answer questions on it. So let's just have a look at that formula in a little bit more detail. In numerical questions, what you're basically going to have to do is figure out what the angular separation is in radians and decide, is it bigger or smaller than 1.22 lambda over b, where lambda is the wavelength. I'm not even going to write that down, you should know it. And b is the diameter of the pupil in the eye. Okay, so this needs to be bigger than this. Okay, in order for you to be able to distinguish, resolve the two objects. And this is a nice picture actually, because this is what happens if the angle is smaller, and this is what happens if the angle is bigger. Okay, and if it's the same, then you can just about make it out. Okay, so that's your minimum point. Now, a note, because it's not quite that easy still. We have to consider this angle in a little bit more detail because it's not so easy to measure. So what usually happens is your eye is here and here are your two objects. Okay, so you can measure that angle. Let me draw that properly, hang on. If we draw this arrangement, you can see that the angle here would be equal to the distance between the two objects divided by the capital distance between the observer, the eye, and the object. Okay, you should be able to see why we can do that in the same way as we've done before. X over d would give us an approximate value for that angle, but because the angle is so small, it's mathematically valid. Okay, so x over d, we can put that over here if the ratio x over d, forget that, is greater than 1.22 times the wavelength over the diameter of the circular hole that's receiving the light, then you're in business and you can resolve the two shapes. So what do we have to worry about? Be careful with your units. Okay, so this distance will be in millimeters. You would have this wavelength times 10 to the, could be anything, minus or plus. Your diameter could be in millimeters. And actually, something to bear in mind, you could be asked, I've seen this in a past paper question, to basically make an approximation of the pupil size. Okay, so what is the diameter of the pupil in your eye? And as you can well imagine, during the exam, candidates were holding up rulers to their eye and all kinds of nonsense. It's best to just remember these numbers. The diameter of the pupil of the eye in a bright condition, a relatively bright condition, can be anything from 2 to 4 millimeters. So remember, that's times 10 to the minus 3. And in a dark room, as it flares and opens up, could be anything from 3 to 8 millimeters. Okay, so it's probably best to just use a blanket value of 5 millimeters. That would be sensible. Okay, normally it's given, but just in case, I have seen questions where they ask you to take a guess. So the last thing we're going to look at is how or what conditions could make resolution easier. So if we look at this side of the equation, the smaller that we can make this, the smaller the angle necessary in order for you to just be able to see things. So if we have a look at wavelength, blue has a much smaller wavelength, so therefore if you have blue light, it's actually easier to resolve, it's easier to see, because you can get, it's much easier for your angle to be bigger than the Rayleigh condition states this side. Okay, so blue light, smaller wavelength, makes resolution happen at a smaller angle, and also making the pupil of your eye, making the diameter bigger. Okay, so by making D bigger, you can bring this down and again increase that resolution at a lower angle. The Doppler effect. The Doppler effect describes the phenomenon of a wavelength or frequency shift when relative motion occurs. So when we have a source that's making or emitting some kind of a wave and a detector D, okay, and there is relative motion, as in case B, where the detector is moving towards the source that's making the noise. Okay, so for example, if you're walking towards an alarm or a siren or something like that, and C, a source which is making sound, which is moving towards a stationary detector. So that could be you on the street and an ambulance drives past you. Now, normally what happens is that you detect a sound, for example, and the frequency that it's emitting is the same as the frequency you receive. So there's no change there.